In this screencast, I'm going to explain how a triple effect evaporator works. And its objective is to concentrate a dilute solution, usually some solute in water, where we use significantly less energy than we would use in a single effect evaporator. So there's a separate screencast on a single effect evaporator that'd be worth watching first that describes the behavior for one of these evaporators in the triple effect. The advantage of the triple effect evaporator is that we can use the vapor from this first evaporator as the source of the heat for evaporating the liquid in the second evaporator, and then we can use the vapor from the second evaporator as the source of heat for evaporating the liquid in the third effect, and I'll go through in detail to show you what we're referring to here. So we're going to have in a triple effect, in the first effect, we're going to have a feed coming in. This is a liquid at low concentration of solute. We're going to vaporize some fraction of this, and then we're going to create a more concentrated solution of liquids. We carry out this evaporation by having steam being fed to these heat transfer coils, and then we have liquid steam leaving. So we're assuming the feed is at saturation pressure. We condense and drip out the liquid also at saturation temperature and pressure. So we have the feed coming at a feed temperature. T1 would be the temperature in the evaporator, which also means it's the temperature of the liquid. And the steam is coming at a temperature Ts, where Ts must be greater than the evaporator temperature for evaporation to occur. So what we do now is feed this liquid leaving the first evaporator into the second evaporator, and we create the evaporation by using the vapor from the first evaporator, and we feed that into the heating coils, and again we get liquid at saturation conditions leaving, and so we're evaporating steam, again vapor phase V2, and liquid more concentrated from the second effect. And then we're going to take this vapor and feed it into the third heat transfer coil. Again, what's leaving is condensed steam, so liquid's at saturation conditions. The concentrated liquid from the second evaporator is then fed into the third evaporator, where we get a more concentrated solution, L3, and we have a final vapor stream coming off. And so we can get a significant improvement in energy efficiency by using the vapor from previous effect to vaporize the liquid in the next effect. So if the temperature in this first effect is T1, temperature here is T2, here's T3. When I say T3, that means both the liquid and the vapor are at T3. Then T1 must be greater than T2 and must be greater than T3 because we are using the temperature T1, the steam, here at T1 to vaporize the liquid in the second effect. So T1 must be greater than T2 for heat transfer. So if we ignore the boiling point rise due to the solute in the liquid, then we can use steam tables to also determine the pressure. So if the first effect is at atmospheric pressure, or 1 bar, then the pressure must be greater than the pressure in the second, must be greater than the pressure in the third, which would mean we'd be running these effects under vacuum in order to create this temperature difference. And the concentrations, we would feed a low concentration solute. There'd be no solute in the vapor phase. We will have concentrated that solute, which is now fed to the second phase, becomes more concentrated and then more concentrated, since that's the objective of the triple effect evaporators. If we assume that the feed coming in is at T1 or very close to T1, then our heat transfer all the energy goes to vaporize the liquid, and we can write the heat transfer in the first effect, heat transfer coefficient, area for heat transfer, temperature to steam minus temperature T1. But this should be approximately equal to the heat transfer in the second effect, because we're going to now condense back all of that vapor that we formed. So Q2, which is U2, area for heat transfer, temperature in the second effect, temperature in the first effect, which is now the heating for the second. And then the same argument means this should be equal to Q3, which then is the temperature for heating and the temperature in the third effect. And typically the heat transfer areas are the same. These are identical evaporators, and the heat transfer coefficient is approximately the same also. And so Ts minus T1 then is approximately T1 minus T2, approximately T2 minus T3. And these temperatures will then determine which pressures we have to operate the effect at to get a steady state operation. The total amount of heat transferred then is Q1 plus Q2 plus Q3, which is going to be equal to UA T of the steam minus T3, this total temperature difference. And so to a first approximation, also 1 kilogram of steam fed in here will vaporize 3 kilograms of our original liquid. And the triple effect evaporator of this type certainly is best used if the feed is hot coming in, so we don't have to use much of our steam energy to heat the feed. And if this liquid here leaving, our product, the concentrated solution, has some temperature sensitivity as we increase its concentration, and we like to be operating that at the lower temperature. The actual calculations are really very similar to those for a single effect evaporator.